for the week 16, well, we still have class, but it's like it's we will not have like new material just for the reviews. Okay, so oh, is anyone just comes in again? I mean, now it's so we have 11 students here. So students who haven't typed your name inside the chat box, you can let me know you are here because I we have to do the attendance check for you. Oh, 09. Okay, yeah, I found you. Okay, so let's see. So I'm going to have a screen sharing for you guys. So here is the, let me see. So so also I have upload the sample exam for the finals in our share folders. So here I just want to let you see like how is the finals looks like. So actually, I think if you finish Dr. Zhou's final exam in the last semester, so actually I think you should have some concepts like how is the final exam looks like. So here I just want you to see like so this file is already in our share folders. So I mean the common share folder. So if you every time you do the homework, you will find it using these share folders. And so this is what our finals would look like. And so it actually, so we'll have like, so five questions for the filling the blanks. And so, I mean, for the questions here, so it won't probably be the same, even similar types, but it's actually like we have 5 questions and it will cover all the materials I am talking about in the in our class. And then we will have like 6 multiple choice questions. So everything is like, so here is I will try my best to make sure we cover everything here. Okay, so it's like, and then we will have the calculation problem. So this is pretty similar to what we have in our midterm. Actually, the difficulty level is kind of, I will keep it at the basic level. I mean, different from what we have in our midterm, because the midterm we only have like the material for the half semester, and I don't have the application questions, and I don't have any proof questions. So just for the calculation. So if just for the calculation, so I have to make some question looks a little bit difficult than the others. So actually, so I mean, I have some. So for the midterm, I have some entry level calculation questions, and some medium level, and some maybe I don't think they're difficult level, but I mean, actually, maybe for you guys, it looks like a little bit difficult. But let's see. Okay, so I mean, but how? I mean, for here, I mean, for the finals, it's definitely will be the entry level and the medium level for the calculation questions. Okay, so you can look at all these questions here and see, okay, whether you can do the calculations. And actually, if you feel like so this is kind of a little bit difficult, you can ask questions like whether you can do or not, and maybe in the week 16th, and let me know, and I'm going to see like whether you have to know the concepts, or is like sometimes it's fine, I'm not going to cover it. So, and then so you can see here is like, so yes, actually, so definitely we'll find like the first order linear differential equations, right? The px qx, actually you have to know how to do it. I mean, this is pretty easy. And then it's gonna be have the calculate the limiting questions. So for the limiting questions is like, so actually we might don't have a lot of the training here, but so just look at how this, I mean, how these limits work. So actually our finals is not going to extend higher level calculations here. And then for the partial derivatives, so usually it's like we won't have very difficult or complicated question. So let you calculate the first derivatives and second order derivatives. So it's like, so maybe you start like here. And then you will also have some partial derivative question. So actually, why this question here? So it's using the chain rules, right? So now it's like, if you can see here, so we have two different things, right? So for the partial derivatives question, so it's probably you have the using the second order and first order, second order derivatives, and also you will have the partial derivatives, which use the chain rules. And then, so for here, this is the geometry vectors and the geometry questions. So this question is kind of not that familiar with you guys, because I don't have a very detailed example for this type of question, but we do have, right? We do have some questions in our, actually you can see the similar types of those questions in our midterm examination. So you can see those things there. So just keeping in mind that you just look everything in our in-class practice and the homework. So actually we'll have the pretty similar types of question for the geometry and vectors, right? And then here will be the next part. This is called integrals. So actually, so we will have maybe we'll have within the rectangular area integral, and maybe sometimes it's maybe different types of the integrals. So it depends on like what kind of the materials I want to cover. So, but I just want I want you guys to know that. So this integral is easy enough, but we might have more difficult level questions here. So it really depends on like which part I want you guys to earn the points, and which part is going to to maybe take some points from you guys. So it is like, so it really depends on what's the expected final examination, final grading I'm gonna to give you. So then we're going to the applied problem. So applied problem. So usually, so it is not just something like it's like, so the how to say, just you have to understand what the question really means, and you have to using the technique or the mathematics skills you learn from the class. So here usually a very typical question is to find the local extreme values. So this question is local extreme value without the constraints. Okay, so if you look at this, so at least you have to understand like half of this, because so for me usually I'm going to make this problem into two parts. So one part is unconstrained extreme local maximum or local minimum, and the second one is going to be the local minimum and the local maximum with constraints. Okay, so we are going to discuss this part today. So this kind of question is, I think is kind of easy for you. Okay, so then, and the other question for the applied problem is we're definitely using the double integral. Okay, so it is like, so if you can see here is like the area of region are bounded by so it's not looks like a rectangular double integral. So it's kind of like it's like you have some restricted areas. So for me it might be so if you just keep in mind that when we're discussing this part, so it's like, so if I want to increase the difficulty levels here, and I'm going to give you something like you have to transfer. Okay, so transfer the coordinates from the Cartesian system to a radian system. So it's like, so a polar system. Okay, the polar coordinate system. So it is really depends on how I'm going to do. So just keep in mind what all of these questions looks like. So although they looks the same, but it depends on like what kind of in-class practice I give you, and depends on what kind of homework I'm going to give you. So just please keep in mind like what all of these questions going to be. Okay, so then in the part 5, so it's going to have some proof questions. So the proof question here is like, so don't think that these questions will be very very hard to do. So I mean, so here is like, so actually, so because we don't have enough question for the to training for the proof. So here I'm going to letting you guys to know is we are going to restrict our proof into two different sections, two different parts. So one question is restrict inside the geometry and the vectors in geometry. So we are going to have some proof question for to see whether some about the some corollas or something in the geometry, and the other part is for inside the partial derivative. So thinking something like this. So actually you have a function and you will find how this equation is so satisfied. So usually this type of question. So if you have any questions, so just please go to the share folders and to see how the exam works and how the question looks like. So after we finish all the in-class materials, so I'm gonna to give you how to give you guys some proof questions for our geometry and our geometry question. Actually, is in the week 16. I'm going to give you some sample proof questions there. So it will give you something. It will give you some understanding, quite a good understanding, like how we're going to get a proof question. So technically speaking, so all these proof questions actually they are not proof. So it's so different from what I did in my undergraduate. So for the proof question, so all this proof is not proof. Okay, it's just calculation question. So you have to keep this in mind, that so this is not proof question. They are just calculation question, but it has to the proof question. The proof question has to be one type of question that's inside our examination. So so everything here is I just want you guys to know like what kind of the just because like what kind of the question, what type of the question, and what is the knowledge part I want to have in our finals. Just keep in mind this is just a sample, so everything is not going to exceed. Okay, we're not going to exceed our in-class example, in-class practice, and our homework. Okay, just keep in mind everything you learn. You have to keep in mind everything in homework, in class practice, and in our in-class example. So all the things you have to have understand them pretty well. Okay, so yeah, so here is maybe in case someone doesn't know where it is, just seeing here is like, so I'm already sure having the share folders links here. I think it's just here. Yeah. Maybe this. Okay, so let's see. Okay. Yes, I just let me see. Can I? I need to give you guys. Okay, so I'm gonna to give you guys a link here. So here, so you are going to see all the shared shared materials in these share folders, and actually you have a pretty good connection within this cloud service. So so if you can see here, like so for the share screens, so what you will have is here. So it's the sample example for final. Okay, so in the 2020 to 2021, and this is the advanced mathematics examination. So you will have both the questions and the answers in this file. Okay, so but if we had time, I'm still gonna to do the analysis for this exam for you guys in the week 16th. But if we don't, just if you can solve all these questions smoothly by yourself, so that will be fine for you. Okay, and then that's it. So yeah, so but the thing is, so here I'm still want you guys to know is like, so just keep in mind that, so although although you already see the similar type of the questions for our finals, however, the difficulty level might change. Okay, so just don't think you are, the question will like that. Just maybe easier or maybe more difficult. So please don't. Oh, 22. Okay, just okay, sure. Yeah, I have to count you in, yeah, for the attendance. Yeah, so we are just discussing the so we're just discussing how is the final exam will looks like, and so this is just for the last year, and for this year. So the questions, how the credit is assigned into different, into the, like the filling blank, the multiple choice, the calculation, the applications, and the proof. This one going to change, but the question will change just based on the materials we just learned. So I'm always saying that just you have to be very just focus on the materials we have in our class, and also the homework. Okay, and so for the proof questions, so I'm going to give you some good samples in the week 16, but not for today's class. Okay, so we're going to keep our class materials for, yeah, so we are going to keep our class materials today. Okay, so yeah, so last time we discussed how to find the local, just find the local minimum and the local maximum, right? So for the questions, find the local minimum and find the local maxima. So what we did is we just let's see. So what we did is so what we did is actually is like we are just finding the we want to make sure, right? So the last time, okay, so last time, okay, so here, so what we did is for the local maxima and the local minima. So what we did is we using the fourth order condition. So actually, so when we know that, so we have a fxy, right? So then we set up a first order condition. So we know that fxy, then we have then we take the first order derivative, we set the partial derivative of x equal to 0, and then we set the partial derivatives of y equal to 0, right? And then we find the critical point, right? Find the critical point. So this is step 1. Find the critical points. And then we have the step 2, right? The step 2 is, so we're using the partial derivative to find the second order, right? So then we know that a is equals to fxx, and it's just saying that this, so, and we have the b is equals to fxy, and c is equals to fyx, and d is equals to fyy. Then what we do is we see, then what we do is we trying to figure out what is this function looks like, right? So actually we have to make sure that, right, so this function, or this equation, so this function is larger than 0. And then when if a is larger than 0, so it's going to be what is the, right, so everything is going to increase. So that is the local minima. So when a is less than 0, that will be a local maximum, right? Oh, let me check this for you. Yeah. Yes. So local maximum. Oh yes, I think I'm doing the yes. Yeah, I'm getting the yeah. Yeah, it's correct. Yeah, well, things are correct. Okay, so this is what we did last time. And actually, we say, okay, what about we find something within a region, right? When we are saying something like within a region, what we did. So what we did is, so step three, if it is if step three, it is within a region. So what we did. So what we did is we checked the corner solution. And check, so what the meaning of the corner solution? The corner solution means, so you know you have a, so when you are restricted on coordinates, so the points here. Mm-hmm. Let me see. Okay, so these points, right? These 3 points, they are corner solutions. So when we're saying the corner solution is just, this is a corner solution. So you can follow the steps from the textbook, but you can, simply you can just following my understanding about this kind of question. So one is, the first is checking the corner solution. Second is check the boundary solution. So what's the meaning of boundary solution? So usually it's like, so this is the boundary, and this is the boundary, and also this is the boundary. So for the most questions, so when you want to say, okay, what about I want to check the corner solutions? So most time, so the boundary solution is only, only the thing is, when you are trying to check in the boundary solution, is only check the solution on this boundary. Okay, so it depends on, is it like, so these 3 boundaries have, you have to do them, by yourself. All the thing you have to do them, because so you don't know what is this function looks like. Okay, so most time, so the local maximum or the local minimum you can find, or the global maximum or the global minimum on this small region you can find is on these corners. Okay, and the other thing is the other thing maybe happens within this area. So it just depends on like how does the surface, okay, so like the paraboloid, how the surface looks like. So but the thing is, so we just when we are but the very important thing is, when we are trying to find a local maximum or local minimum within a specific point or within a specific region, what you should do is, using the first order or second order conditions, and then to check the corner solutions and check the boundary solutions. Okay, so the only thing I want to mention here is, so actually, so in our exam, so usually we won't require you to do that. Okay, so like what you can see in our final, the sample question in our finals. So usually is, so for those questions, is like when it won't ask you, it won't ask you to find the local maximum, or ask you to find the local minimum. So usually the only thing they will ask you is for what is the local maximum or what is the local minimum. So usually those questions you see, in a 3-dimensional space. So for the paraboloid, so it's like, so sometimes it's like, so all everything is like this. Okay, so they will have one local maximum or one local minimum. So the question is only like, would only ask you like, what is the local maximum or what is the local minimum. So usually they won't asking you guys, to see, okay, what is the, so we'll ask you simultaneously is like what is the local maximum and what is the local minimum. So that is sometimes it's too it's kind of like complicated. So when if we don't if we don't want to make the question too complicated, okay, so then we will have the Lagrange multipliers. So when we are discussing what is a Lagrange multiplier, so this is a very important concept in our advanced mathematics. Actually, so you will actually in the future you will always using these concepts, the Lagrange multipliers. So it is kind of different. Okay, I mean it's what is different? It's like more usable or practical in our future in the future, because you will always, so I mean when even if you are doing the AI, right, so you still have to find the best value and the highest value or the lowest value or highest score, lowest score, whatever. So and then you will have a constraint, right? So the thing is, so in the real world, right? So you will always have constraints, right? So you have the power constraints, you will have the computation capability constraints. So you have so many constraints. So you have to find a local maximum and a local minimum within that constraints. So this is always what you did in the real world. So what I was saying that the Lagrange multiplier is very important. And so when you are, so in the textbook, okay, so let's see in the textbook. So I'm going to be using a different way to explain the Lagrange multiplier. So although we're maybe this very similar, but it's just, it will be very pretty different. Okay, so still we will have a paraboloid. So here is just help you guys to understand. Okay, if you don't, if you think that the three-dimensional spaces looks like a pretty, it's difficult for you, but so we will have a counterplot in a two-dimensional space. Okay, so here is, so we will have a paraboloid. Okay, so we'll have paraboloid here, fxyz. So we have a paraboloid here, and then we'll have a constraint. So right, so originally we know that, so the paraboloid, so it will have the local maximum. So what we see here is we're just saying here's the local maximum. So however, to have this local maximum, it's very hard for us, because sometimes we have the resource constraints, so we will never get this point, right? So then we'll have this, so we'll have a constraint, right? So the constraint, if this is if we set this 3D dimensional space, okay? So this is our constraint, f, x, y, z constraint. So then we will have the constraint here. So everything, okay, so everything here, so we're only within. So only within this blue part. So the blue part is what we can get. So we have to find the local, the local maximum or the local minimum within that constraint. And then let's see. So so we should, okay. So suppose the plane and the paraboloid, they are intersect at this green line. So we have to find the local maximum on this green line. So we can say that maybe we have a okay. So yes. So let's see here. Using this. Okay. So this is the intersects. Okay. So then it will be this green part is the local maximum with constraint. Okay, so this is how, this part is, so this is not inside our, it's not in our textbook. Actually, they are, I mean, the textbook, they're using the different how to say, different 3D dimensional surface to explain this. So then I mean, if this part is for you, I mean, it's too complicated, then we will try, I will transfer the 3D dimensional space picture into a counterplot. Okay, so then what is a counterplot? I mean, so think about it that paraboloid. So we know that, so this is x and this is y, right? We know that, okay, so assume, okay, so we know that the local maximum, this is the local maximum, okay? This is the local maximum. Or we are saying that this is the global maximum. So, and then what does the counterplot mean, like, right? So, I mean, just to recall what the counterplot is. So actually, so for here, we can say that local maximum z is equal to 4. Then we will find a curve, right? The projection of the 3D dimensional paraboloid and into the 2-dimensional space. And then we will find a curve. Here is z is equal to 3. And then we will find a curve as z is equal to 2. And we will find a curve as z is equal to 1. So, and now we have a constraint, right? We have a constraint. So suppose now we have a constraint. So now the constraint is no longer plane anymore. So this is a straight line. So we have the straight line here. So this is our constraint. So this is counterplot. And this is our constraint. So this is fxy equals to 0. So this is our constraint. Okay, so then so what is the new so what is the, I mean, what is the new local so actually, so let me see. So let's see here. Okay, so what is the new constrained local maximum? So we are trying to find a tangent. Okay, then this tangent. So then here is the local maximum with constraint. So this looks like, okay, so this type of things looks like, okay, so this this counterplot is trying to give you a concept. So what is a constraint, a local maximum and a local minimum looks like? Okay, so then so why this? So we should find a curve, the counterplot, a curve of the counterplot to tangent with the constraint. Okay, so we graph so we have a new graph here. So okay, so this time we have to we fix the constraint. Okay, we fix the constraint here. So we fix constraint here, and then so what we think that, so there are like 3 different, okay, we're saying that 3 different counter curve. Okay, so one is the tangent counter curve. Okay, so let's see C2, and we have the counter curve here. So we have counter curve is don't have intersect with this constraint. So we have a 3rd counter curve. So we know that Z1 is larger than Z2 and larger than Z3. Okay, so this is the counter curve. So actually, you can assume that Z1 is less than Z2 and less than Z3. So this is just it's a counter. Okay, so don't so we just assume here. Okay, assume. So then, I mean, so if you see why we need to find the a tangent line with a counter curve. Okay, so then I mean, so actually, so when you think about it, so if, I mean, this is your, so suppose this is your constraints. Okay, so if you find that, so if C3 is the local maximum value. So actually, so if you choose this, I mean, if you choose the xy at this point, and you think z3, okay, this is the local maximum value. However, I mean, you can, these points, okay, can move around. So point under constraint can move around okay, to a higher value. Okay, did you see that? So actually, so it can move along from the Z3 to Z2. I mean, on this, along this constraint line. So which means, I mean, with this constraint, you can find some is higher, okay, something higher. So you can know that, so the old point is not the constrained local maximum, right? So, but if you want to choose a point on the Z1, however, all the points on the Z1 is outside of the constraint. So you can you cannot you cannot find a point on the Z1 which satisfy the constraints. Okay, so this is usually what we so this is why we need to find a tangent line. Or I mean, in a three-dimensional space, it's going to be a tangent plane. So if you have like more than three, like 4 or 5, there's going to be a tangent hyperplane. Okay, so just for this class, so I mean, we only have I think we only have three-dimensional space, right? So we not exceed three-dimensional space. So the constraint is in a three-dimensional space, it's just a tangent plane. But if we project this into a counterplot, then the constraint is going to be a tangent line. So here is going to tell you why. I mean, it's not saying mathematically, but logically telling you guys why this has to be a tangent line. So then it's like, so as long as like we know that this is a tangent line, so what we have, so it's like, because this is a counter, right? So this is a counterplot. So actually we know that this is a tangent line, and then we also know that, so the gradients, right? So the gradient is here. So the gradient is, so this is the gradient. So I mean, geometry, we know that this is a gradient. So what is a gradient? The gradient is the quickest direction, right? Where the function is going to lower its value. The farthest way to lower its value on that specific point, right? So then we will have then we want to introduce, like, so we know that, so let's see, so fxy, so we might, okay, so the constraint, okay, we just using the constraints here, using G, constraint using G and G. Okay, so then we have to understand that, so our f, so the surface, the gradient of that surface is going to have to be, it have to equals to the has to equals to the gradients of our constraint. So okay, so this is, so because I mean, so because so actually from this tangent line, you know that, right? So the gradients is the direction of this tangent, and then you have the, I mean, the tangent line of the tangent of the constraints, right? The tangent of this constraint. So they have the, so actually they may have the same direction, or they might have the opposite direction. Okay, so then the Lagrange multipliers. Then we are just introduce the Lagrange multipliers method. So suppose, right? Suppose we have an fxy. And we want to find the maximum or minimum value subject to gxy equals to 0. And then we can write down the function f x y lambda is equals to fxy plus lambda gxy. So this is the Lagrange multiplier with one restriction. So if you have two restrictions, you can adding more restrictions here. So for this class, it's like we only have one restriction. So if the restriction is more than one, then we can write down is f xy lambda I is equals to fxy plus sigma lambda I and gxy. Okay, so this is just so for here is like, so this part is not important. Okay, this part is extension, so you don't need to think about it. But you have to understand, so what kind of the Lagrange multiplier you have. So if I only have one restriction, okay, so what I can do. So then the thing is here, okay, so in what kind of the condition, right? So in what kind of the condition I can definitely using the Lagrange multipliers. So here, I mean, if you can see here, like, so in the counterplot, right? In our counterplot. So in our counterplot. So I mean, when I'm trying to explain what is the Lagrange multiplier is, so in our counterplot, we will find that our local maximum or local minimum, actually the point is outside of the constraint. So which means, so along this constraints is works. Okay. However, if the local maximum and the local minimum is here, what if the local maximum and the local minimum is here? So actually, the local maximum, actually the constraints doesn't apply to this local maximum and the local minimum. Okay, so when you are doing the so the thing is very important. So when you are trying to do the local maximum and the local minimum, you have to find those critical points and to see whether this critical point is inside of this constraint or this is outside of constraint. Because if it is outside of this constraint, which means this constraint doesn't work, so that you don't have to introduce the Lagrange multiplier into a solution. However, if the critical point is outside of the constraint, then you have to use the Lagrange multiplier. But in our class, when we are trying to, what we are trying to do in our finals, okay, just for this class, is like, so you don't have to check. So you don't need to check, whether this point is inside of this constraint or outside of the constraint, because when I'm saying, okay, please find the local maximum and find the local minimum and subject to some condition. Okay, so it's already assumed that if without constraints, so you will have a better solution. Okay, you will find a better answer, or find a higher value or lower value than your constraint maximum or minimum. Okay, so this is what I want to mention, but this is so kind of you can treat this also as extension. Okay. So in our finals, we're not trying to let you guys to classify whether the critical point is within the subjects within the constraints, or so actually it's just like is subject to the constraint, or that is not. Okay, so whether the constraint works. So in our final we won't, but I mean in the future, if you do want to know, right, only find the answer. So because sometimes when you are trying, when you are so actually, so because I mean for now, I mean maybe in the future you will find a you will have a, how to say, is find a, you have a better method. The constraint is no longer just a line. Actually, the constraint is going to be an area. So and in that way, you will have some better techniques to do that. But for now, that's not okay. For now, that's not, because it's going to we have to have a better understanding for the border Haitian or Haitian. So it's like just outside of the materials of this class. So, but just want you guys to know, like, right? So the constraint is not always just works. Okay. So, but okay. So then uh, so let's see. Okay, let's see. Let's have some examples, like to see how is the Lagrange multiplier works. Okay, so we will have the. Okay, so let's see. So for the example one, yeah. So I mean, don't. So for me, it's like I was saying that when we are discussing the Lagrange multipliers, just please don't think of just don't using the textbook. Only the textbook is, I mean, when I'm looking at those, looking at uh, the question instead of our textbook, actually I feel like they are actually they makes the question kind of like more complicated. Actually, if we are just using the very pretty pure algebra ways, we don't saying we have the if we don't think about the geometry ways, so we just only think about algebra ways. So I think that's a much easier job to do. Okay, so let's see. Let's see in the example. So example one here. So let's see. Oh, okay. So the question is, so let's suppose XYZ is the length, width, and height for the rectangle. I think it's a rectangular. Yes, rectangle. So respectively, and find the XYZ, which minimize the surface area of the rectangular S is equals to 2 times XZ plus YZ plus XY, subject to the condition XYZ is equal to 2. Okay, so this example is, like in a 3-dimensional space. Okay, so usually we only like, so we have like a 2-dimensional space, but we're just saying that, so it's like, I mean, the thing is like pretty similar. So what we can do is we'll have the solution. Okay, so the solution here is we can let the big F X Y Z lambda is equals to 2 times fxz plus yz and plus xy, and minus a plus lambda times the xyz minus 2. So for this part, so this is the, so then we are just, I mean, we are constructing what is the Lagrange multiplier is. So let me see. Okay, I think I may. Okay, okay. So and let the xyz lambda is equal to 2 times xz plus yz plus xy plus and plus lambda times xyz minus 2. Okay, then what we do is following the so something such as the without the says fx is equals to the I mean, we take the partial derivative of x, right? So then is this equals to 2z plus 2y plus lambda yz is equal to 0. And then we take the partial derivatives on fy is equal to 2z and plus 2x and plus lambda times xz is equal to 0. And then we have the fc is equals to 2x plus 2y and plus lambda xy is equal to 0. So then we have the f lambda is equals to xyz minus 2 is equal to 0. Okay, so then what we need to do is trying to, to find the xyz. Okay, so then, so here is what we know here is I think so although, I mean, for me, I think it's pretty easier because the fx, fy, fz, I mean, actually they are the same with each other. So for here is actually the only thing is it should be like x is equals to y equals to z. Although, I mean, you might have the difficulties to solve this equations, system equations. So yes, actually, I do have. I do think that you might have some calculation. May have some calculation problems here. So yes, I mean, the only thing, I mean, here is like the fx, fy, fz. Actually, they are similar. That is actually the same. When you are observing the system equation, you will find that so x, y, z actually within this equation they are actually they are substitution. So what you can do is, so here is, that x, y, z, they should be the same. Okay, so they should be the same, but whatever. I mean, just let's do this question. Let's do this first. So what you know is, so actually, so what you can do here is, that, so actually, so that x is equal to y and equal to z is equal to 2 with the power of the 1/3. Okay, so this is the, and so when you are doing this type of the question, you have add here because this is application questions. Okay, so when we're discussing the Lagrange multiplier here, the first step one is we writing out the Lagrange multiplier here, and then we're writing out the Lagrange multiplier, the function of our Lagrange multipliers, and then look like what we did in defining the local maximum and local minimum. So we're taking the partial derivatives under x, y, or the including the lambda. So we're taking the on each independent variables here. So each independent variables here, so x, y, z, and lambda, and then you have to calculating. So you are setting up these first order condition equal to 0, and then you should find the critical point here. Okay, so then before you're saying that this is a local maximum or local minimum, you're just saying that because this is a real application. So then we will have the local minimum here. Okay, so because if you don't write this, if you don't write this sentence, then you will have to do so. This question, so this sentence actually is a Hessian matrix. Okay, if we have a Hessian matrix here, so then you have to using this Hessian matrix. So what do we have? So it's like fxx, right? fxy, fxz, and fx lambda. So fyx, fcx, lambda x. So actually you will have using this Hessian matrix. Okay, so this is not required. Okay, so this is not required in our class. Okay, so just skip out of this Hessian matrix. This is too complicated. So we're just saying, okay, so because this is the application questions, then we will have the local minimum. That's enough. Okay, so you have to always keep this question here. Okay, so now in our finding the local maximum and finding the local minimum using the Lagrange multipliers, or using the if we want to using the local Lagrange multiplier, if we want to using the constraint such as the Lagrange multipliers, or if we want to doing the local maximum minimum questions without constraints. Okay, they are like two different type of questions. Okay, so let's see, what about the example 2? So suppose for a company, suppose a company has a sales income R, and the advertisement fee X. So sorry, sales income R, and advertisement radio X and the advertisement B for newspaper Y, and the relationship three above is R is equals to 15 plus 14x plus 32y and minus 8xy and minus 2x squared and minus 10y squared. So the first question is, so without budget constraint, what is the best strategy for the advertisement? So if the budget constraint is 1.5, what is the best strategy for the advertisement? Okay, here is to maximize the sales. Okay, so now, so for here is, so we have, so this is a pretty, pretty important. What about, saying that about our, so actually is the question, for the, if I do want to have a question for you guys, to do for the local maximum and local minimum and with and without the constraints. Okay, so the first question, so we have, actually, this is the application question. So actually we have a company that has its sales, and the sales, it depends on its advertisement fee and the combination of advertisement fee. So it depends on the newspaper advertisement fee and the radio advertisement fee. So we want to find a best. Okay, so based on the, based on the some mathematical function, we know that, so there will be a best. Okay, so there will be a best, so what is a best solutions? So it should be a best solutions. Usually that is for the what to say is like, so as the best solutions for like what is the combinations for the newspaper and the radio. However, for most companies, they don't have enough, how to say, they don't have the enough budget, to put, to enough budget to do the advertisement. So you have to find a local maximum or local minimum within the constraint. Okay, so all these things, it's like, so you have to do this, this is like so I'm saying that this example is pretty important, right? So it just depends on, like, it looks pretty similar to what we discussed in we discussed previously for the final exam, for the sample final examination, right? So then what do we do? For the for the one, so for all these kind of, for all these kind of the questions. So if you feel like your, if you feel what the question wants you to do, Okay, so it's like just keep in mind. So you have a relationship, for fxy, the c equals fxy. So here is r is equal to fxy, right? They're the same. You're just doing the same thing here. So so for the solution, without, we're saying, okay, you know that we are without constraints. Okay, without constraint. So without constraints, so what you can do? So without constraints, let me see. Let me see. Okay, so here is the to maximize the profit. So, so here, so for these questions, okay. So the first thing is, so because this is application, right? This is application. So without constraint, so what is the profit? Profit is actually equals to the the sales minus the cost, right? Sales minus the cost. So the sales minus cost. So what is the sales? Sales is the R. So R is equal to 15 plus 14x plus 32y and the minus 8xy and the minus 2x squares and the minus 10y squares. Okay, then this part is the sales. Okay, so then we are going to minus the cost. The cost is x plus y. Okay, so then we are doing the find the local maximum or finding the local minimum without constraint. So then we can say that the big fxy is equals to 15 plus 14x plus 32y and then minus 8xy and then minus 2x squares and minus 10y squares and then minus x and then minus y. And that is equals to 15 plus 13x and plus 31y and then minus 8xy and then minus 2x squares and then minus 10y squares. So then we can taking the first derivatives, right? Then we take the first derivative is fx. Fx is equals to 13 and minus 8y and minus 4x is equal to 0. And fy is equals to 31 minus 8x and minus 20y is equal to 0. Okay, I think you guys can solve this system equation, the system equation easily. Okay, so then we know that x is equals to 0.75 and y is equal to 1.25. So here, no, so the critical point, then we find a critical point. Is 0.75 and 1.25. Okay, so and then what we do is, so then we have to do this is fxx. Okay, so a is equals to a is equals to fxx is equals to -4. B is equals to fxy is equals to -8, and C is equals to fyx is equals to -8, and D is equals to fyy, that is equals to -20. So A, B, C, D is equals to 80 minus 64 is equal to 16, which is larger than 0. And then we know that fxx is equal to -5, which is less than 0. Then we find the local maximum when x is equals to xy is equals to 0.75 and 1.25. So then, I mean, you can, and the local maximum is let me see. So the local maximum is, oh yeah, I might just, yeah, I need to use the calculator to try to see what is the local maximum. So the local maximum is, so the local maximum is 39, 30, okay, is 39, or just saying that 157 over 4. Okay, so this is the first part. The first part for our for what do we find the local maximum, or for the local minimum. So this is for the application. So for the application questions, and then I mean for the second part. So for the second part with the solution. So for the second part, so now we have the constraints, right? So when we have the constraints, so I mean here is like we are using the Lagrange multiplier, right? So when we are using the Lagrange multiplier, so we'll have to, so I mean in the real problem, we'll have to using the equation starting at, so this is a L x y lambda. Okay, so here is, so L is the meaning for the Lagrange. Okay, so Lagrange multiplier, so is equals to so here is still is equals to the profit function. So the profit function is here. Okay, so this is the fxy, right? So the profit function, okay, so profit function fxy, and minus lambda gxy. So the gxy here is, we know that, so we have, because the constraint is, so we know that the constraint here is like the budget constraint, right? The budget constraint is 1.5. So what we can do is, so we know that the fxy is equals to 1.5. So gxy is equals to x plus y minus 1.5. Okay, so we have, so I mean, the plus or the minus here is not that important in this part, because the lambda could be the negative or could be the positive. Actually, the lambda is kind of a parameters, you know, is a parameter which is kind of actually is a compensation. Okay, lambda actually is a compensation for how is the budget constraint moves. Okay, so it's like how the budget constraint is pretty far away from the original local maximum, is very close to the local maximum. So whatever. So we are just think about that. I mean, the lambda has different means. Okay, has the different meanings in different questions. But here we're just saying that it's just a common parameters here. So then, so the question is going to be is equals to 15 plus 13x and plus 31y, and then minus 8xy, and then minus 2x squares minus 10y squares, and plus lambda times x plus y minus 1.5. Okay, and then we just, okay, then we can, what we can do is we taking the partial derivatives on x. Okay, partial derivatives on x is equals to 13 minus 8y and minus the 4x and plus lambda is equal to 0. And Ly is equals to 31 minus 8x and minus 20y and plus lambda is equal to 0. The third is we are just doing the Lagrange multipliers, do the partials on the lambda is equal to x plus y minus 1.5 equal to 0. Okay, so when you are seeing this type of the question, what you can do, actually you just, let the Lx, so you let the Lx, so I'm trying to lead you guys like to solve how are we going to do this. So Lx minus Ly. Okay, so that is equals to 3 minus 1 is negative 2. 1 minus 3 is negative 22. This is the negative 18. And negative 8y plus negative 8y. So that is will be plus 12y. And here is plus 4x and the lambda that's going to be 0. And then we know that L lambda is equals to x plus y is minus 1.5 is equal to 0. And then here you can know that x is equals to 0 and y is equals to 1.5. Okay, so actually, so this type of, so when you are trying to solve this kind of a question, so in our finals, if I want you to solve this type of question, so actually I'm going to make sure, okay, it is kind of easy. It will not depend too much on your calculation capabilities, actually. So in our actually in for the advanced mathematics, so you are not allowed to using the calculators. Okay, so we are not allowed to use the calculator. So I will trying to make sure the calculation is like always. So the calculation is as simple as enough. Okay, not say too simple. Okay, so just like, okay, you make sure that, okay, when you have a question, the answer is an integer, that will be fine. Okay, so here is like this for example. So it's just don't be too afraid like how is the calculation is too difficult. But in our finals, usually like all the question, the solution is will be the integer. Okay, and then we know that. So then you have to add a answer here is because according to the this sentence is not fixed. Okay, you just have to let me know that you know that when you are thinking this is a constrained local maximum or minimum, you have to say this is because this is the application question according to the question. So the application always has a solution for the local maximum. Then so y equals to 0 is the solution. The profit is, so when you're calculating the profit, what you do is you always still using the using the same thing here is like you just put in the x equals to 0 and the y equals to 1.5, and inside of this is 39. Okay, so then you can, I mean, then you find that, so here is like, so, you know, so this is how are we going to solve the question, for the local maximum and the local minimum without the constraints, and how we're going to solve the local maximum and the local minimum with the constraint. Okay, so when we are discussing the application questions, so if we don't have the constraint, so actually you have to apply everything here is like, so because we don't have constraints, so you have to give out the distinguish. So you have to give out this part. Okay, you have to give out this part. So what you need to do is you have to give out. Okay, you have to give out this part. So it's like, because it's unconstrained. We already discussed. I mean, I will fix the independent variable into only have x and only have y. Okay, so then when you are discussing the critical point, whether it is a local maximum or whether this is a local minimum, you have to use in this part to check whether it is a local maximum or local minimum, or it is a set of points. But I mean, the question assure you it is either a local maximum or a local minimum, but you have to give out all the full process. However, when things goes into the Lagrange multipliers, so you have to make sure you already say, okay, why this is a local maximum or local minimum. So you don't have to using the mathematical process, but you have to mention that because this is a real question or real application questions, so you definitely have a local maximum and a local minimum here. So yeah, we don't need to write out the true Hessian and the true Boulder Hessian to prove that the local maximum or the local minimum exists. Okay, but whatever. So here is like you have to make sure it's always keep in your mind this sentence is pretty important. If the question is have like 8 credits for this question, is this sentence is going to worth 1 point. Okay, just this question is going to worth 1 point, even your solution is correct. Okay, so that's actually this is everything I want to discuss for the Lagrange multipliers and the constrained and unconstrained, and find the local maximum and the local minimum with the constrained or unconstrained conditions. So we will have more. Let me see. We will have more samples, examples in our review class. Actually, it should be like in the week 15. So to see how to do this type of the questions, but give you more trainings there. But for now, I'm going to discuss where I have to go into the integral, the multiple integral part. So we will have so let's have like a 10 minutes break for now, and after we come back, we are going to discussing the multiple integrals. So after the break, okay? Yes, see you in 10 minutes. Okay, so let's go back to the go back to our class. So here is, so we are going to, so for the partial derivative part, so we only, so everything we're going to, so we already finished all the materials I want to discuss with you, and the textbook still have something about, such as in the Taylor expansion series for the two variables. If you have the if you do want to understand or have the questions, I mean, to understand what's the Taylor expansions there, uh, you can ask me after class. But for now, it's like this is not in our class materials. But I still think that part is kind of important, because the Taylor series is also a very important thing you are going to use in your future study, because it is kind of a way, to transfer how to say, just transfer the function, okay, transfer a function to a series. So because sometimes the function is not good enough to try to describe its characteristics, but if it can be transferred into a series, and it's going to help you guys, to understand and describe the characteristics of this function. So it's really pretty important. I mean, even in the future, you will use this kind of the characteristics. Okay, but it's not in our discussion materials. But if you have time, you can just scan it and just seeing if there's some, scan it and just to see if something that's to help you. Okay, so then what we want to do this semester here, I mean, in the next part, is the integral. So yeah, so what we want to discuss here is the multiple integrals. So previously, I think in your how to say is in the last semester, in the fourth semester, so you already have some knowledge for the integral. So at that time, I think if Dr. Zhou gives you the concept of the integral, it actually is you have to cut the function into very, very small pieces. It's called the double summaries, right? So, and what you can do is like now you have a very, very tiny line, right? Then now it's going to be a pretty tiny, like something like a cubic. So it is like, so now you are summary those things, not say along the line, but you are trying to summary those small things is on an area. So it's no longer on a line, but this is on a surface or on an area. So that is something like called multiple integrals. So the first is we are going to be discussing the double and iterated integrals over rectangles. Okay, so the first thing is about so now we want to, so the thing is still like, so going back to think about our geometry and our partial derivatives. So we're already discussing how is the surface looks like on a three-dimensional space. So now we are not trying to so no longer trying to discussing what is the surface looks like. Okay, so now we are trying to get what is the volume of that surface. So sometimes when we are looking at the surface, so it is very hard. It is very hard for you to calculate the volume under the surface and above the XOY plane, right? So then I mean, going back to think about what is the one variable single integral. So one variable integral is like you want to, so what you calculate is the area, right? Area under the data, under the function, the curve, under the curve, and between the x-axis, right? So now, I mean, so the multiple or the two-dimensional integral is trying to calculate the volume under the surface and above the x or y plane. So this is trying to extend the integral concept from a one-dimensional place or from a two-dimensional place into a two or three-dimensional space. So now, so actually, so when you see the integral, I mean, when you see the plot here, so now is you are you are trying to think about this is a kind of like projection from the three-dimensional into the two-dimensional. So now actually is, so it's like, so if you have, right, you have a, so if you have a paraboloid surface here, right, and what you want to do is you want to see what is the projection of this paraboloid point onto this x or y plane. Okay, so let's see, it's just like this, like this three-dimensional plot. Okay, so what you want to do is you want to project this paraboloid and to find what is the projection of this paraboloid onto the x or y space. So, and this is, and when you want to calculate the volume under this surface, so you are trying to actually to sum up these rectangulars. So when you are in a, if it is a integral in the two-dimensional space, it's just a curve under the line. You are saying, okay, I want to add up all these small lines, right? I want to add up all the small lines, the value of all these small lines along this x-axis, and then now it's like you are trying to sum up all these rectangulars and on this projection, okay, to see on these projections on this projected area. So if the rectangle is small enough, so like what we have here. So here is like you are trying to add up these, right? This rectangular here, right? So when this rectangle is small enough, and then it's just going to be the integral, and then you can calculate the area under the curve precisely. And for the three-dimensional space, or for the multiple integral, we are trying to make this rectangular as small as possible. So when you are adding those things up, so what you can do is you will get the volume under this surface. Okay, so this is just an extension concept. Okay, so then we can do it here. So what the volume is when the n is going to the limit. So the n is the number of those these small rectangulars. So it's the small rectangular boxes. So here is the n is the number. So actually, so when you divide these small rectangular boxes into a very small, when they're going to in a small enough, is also making the number of n is going to infinity. So then this is going to be the multiple integral. Okay, so this is going to be the concept of the multiple integral. So the delta AK is just so if you can see, just this small rectangular. So if you are making the small rectangular or the small square really small, okay, so and then the number of this rectangle is going to be big enough. So what we can see here is, so we are trying to using the average value of z, to simulate how the surface looks like. So so just about this surface. Okay, so when we are using 16 rectangular boxes, so the surface looks like in this way. And when we are making the rectangular boxes to 64, then it's this way. And when we are going to make let the rectangular box into 256, so it looks like, okay, the surface is, you see, the surface is much more smoother than before, right? Comparing the 16, 64, and 256. So as long as we keep increasing the number of these small rectangular boxes, I mean, so the more likely, so the small rectangular box is going to describe the smooth surface well. Okay, so this is, so then we can see here is like this is the theorem, like when we are trying to calculate the how is the integral, the multiple integral looks like. So here is, so suppose that we wish to calculate the volume under the plane z is equal to 4 minus x minus y over the rectangular region R, which is 0 is less or equal than x is less than or equal to 2, and then y is larger than 0 and less or equal than 1 in the xy plane. If we apply the method of slicing from section 6.1, where slice is perpendicular to the x-axis, then the volume is, so if you can see here, then the volume is, so x equal to 0 to x equals to 2. And then we're doing the integral is ax dx. So if we see the slice here, so this is the slice here. So what we did is we are trying to add up all these small slices, right? We are trying to, let me see. Okay. Yeah, so we are trying to add up all these small slices. Let me see. Oh, sorry. So yeah, so we are trying to adding up all these small. So we are trying to add up all these slices. So here is yes. So let's using that. So, and here is we know that how this slice, how the small slice looks like. It looks like it's like we are. So it's like, so we are just trying to, to do the same thing, do the same integral, right? So we are doing the integral into two separate cases. So So the first step is we are trying to say, okay, this volume under the x, so that the volume under this surface. So the first thing is we are assuming that, we are trying to add up those small slices along the x-axis. So it is like just saying, I mean, if you just looking at this surface from the XOZ plane, okay, see the axis from XOZ plane, then there is like, so the small slices is just actually is just a segment, right? It looks like the same as what you can do it inside the integral, right? The one variable integral, the one variable integral. And then after that, and then you are just, I mean, you how to say, it's like you are seeing this XOYZ, the three-dimensional coordinate system into the other way, and you are saying that, okay, now the slice is not just a segment now, it's more like it. So it is a kind of like a two, what does this look like? Not rectangular, so I just don't remember what it is. But it's like, so you are doing another way is you are doing the ax, you are also doing the one-dimensional integral. Okay, so it's like, so from the x equal to 0 to the 4 minus x minus 1, and then you do the integral from the 0 to 1, right? So this is so you are trying to add up. So you are know that for each small slices, so what is the area of these slices? Okay, so the area doesn't have volume, so that this small slice is too small, small enough. It's like, so the height, so there's no height for this small slices. Okay, so then the same thing is like, so you can do the same thing as like, so now you are trying to, right? You are trying to fix the y, and when you are fix the y, is like, so you are gonna do y is equal to 1 to y is equal to 0 to y is equal to 1, and the ax here now is ax, right? Ax and dy, right? So now it's like, so from here we can see that, so for the multiple integral, we can integrate it from the x, or we can say, okay, we can integrate from the y. So these two are kind of the so the order is, I mean, at least for this example, like we can, so you can either integrate the x first, or you can integrate the y first, and then you integrate them together. Okay, so then what we can do is we find the Fubini theorem. So this is the first one. So fxy is continuous throughout the rectangular region. So R is A is less or equal than X and less or equal than B, and C, then the Y is belongs to C to D. So the double integral fxy on the area A, on the area R and over the A is equals to the region R. So it's equal to, so from, so actually, so here you should be very careful. You see here, ax is less, is ax is A to B, right? Y is C to D. So, and you see here, so you have the integral here, okay? So you have the x, so the integral area of the x is from A to B, and then you have to integral y. So y, the area of a y is C to D. So keep in mind, so this is very important. The order of the multiple integral is very important. So for here, you integrated x first, and then you integrated y. And then, I mean, to look out the second part, to look out this equation, and you find that, so now the first is you integrate the y first, so then you find that the region here is from C to D, right? Then you integrate x, so the region of x is A to B. So this is really important. You know, the order is really important because if the function of the, you know, on the two-dimensional space, the function on the three-dimensional space, if the function is not continuous, right? Sometimes we see that the function is not continuous. Then if you change the order of the integral, you are going to get different answers. So it's like, so although here you see that, okay, you can change, right? You can change the integral order, right? You can integrate it x first and then you integrate y, or you can integrate y first and then you can integrate x. But this is not always there. So this is not always true. Okay, so for our class, you can assume this is true, but this is not always true. Okay, so this is, you have to make sure of that. And then, so let's see what we, this is the example. Let me see. This is the example for the example one for the so how is the multiple integral looks like within a rectangular area. Okay, so let's, I mean, before we goes into the algebra, so I mean, as I always say that we are not going to ask you too much about how this integral works. So let's see. So we know that, so z is equals to 100 minus 6x squared times y, right? 6 times x squared times y, and the region of x is belongs to 0 to 2. Okay, so at the area of x is 0 to 2, and the area of y is from -1 to 1, right? So then, I mean, just looking at I mean, this is the domain. Okay, so we're just saying that this is the domain of the fxy. Okay, and then we want to see the value. The value is, so the value is just the green surface. Okay, so when you are trying to calculate the volume, okay, so what the integral is, you are just trying to get in the volume here. Okay, you are trying to get in the volume here, right? So you are trying to get the volume here, and this is what you can have. So then, this is just give you a concept, like what is the integral we do. Okay, so then here is the example. So this is the example 2. Okay, still the same thing. So we have this surface. Okay, so then we have the domain of x and y, which is a rectangular, which is a rectangular. Okay, so then doing the double integral is trying to find the volume under this surface. Okay, so then let's see. Okay, let's see how we're going to solve this type of the questions. Okay, so for using the double integrals. So example one. So actually, what they want to calculate. Yes. Oh, yeah. The screen, the sharing screen. Just give me one moment. So if I mean this is so I mean for the double integral we are always trying to do the so what we are always trying to do is trying to get the volume. Okay, so when we are trying to get the volume of this of the question, so it's like so if so now for now it's like so you can if you are if I mean if your geometry is good, you can try to think about how is this thing looks like, right? So if your geometry is not good enough, so it's like you're just saying, okay, so what we do is we just so you have to do is just I mean algebraic, okay? So that is like so we're just having the R and then we have the fxy, right? Fxy. And we know that so this is and we know that this is a rectangular, right? So you know that the area is a rectangular, then you do what you do is you do -1 1 and you here is a 0 2 and then here you put the fxy here. So 0 2 is x, so you have the x here, and -1 1 is y, you have a y here. Okay, so here is this is the integral integral here the first, and then you integral here. So there, so actually, so you have so the area is really important. Okay, so when you have x here, so you have to so if you think this kind of the notation is really is kind of like so how to say it like it makes you feel confused. So you have the other way to write it down is like you can write it here. So you can say okay, -1 to 1 is dy, and here is 0 to 2 and fxy dx. So why we can write these things like this down here? Because when we are only doing the let me see how to say it. So when you are doing the let me think about it. If I can let this show this to you guys. Yeah, I'm trying not to make you feel confused. No. Just we don't use this type of notation. No, we don't use this. Yeah. So why we can do that? Because when you are integrate on x, it's like you are already fixing y. So for now, is y is just how to say y is just as a constant. So here, so when you are doing the I have to make sure. So when you are doing the integral fxy on x, is so x is variable, y is constant. So this is pretty important. So why? Because it's like so it is like just so you have to try to think about this is a type of the like a partial derivative. So this is a inverse or a reverse concept of a partial derivative. So when you are doing the integral, so if we are doing the integral on you are doing the partial derivatives on x, so fxy, you are doing the partial derivative on x, you are assuming x is a variable and y is a constant. And for the same concept here, so if you are trying to do the integral, so now on x, so then x is a so actually so x is a variable and y is a constant. So now then let's keep doing this. So n1 0 2 and 100 minus 6x squared y, and that is dy dx and dy. So here is we're just doing the things as the just a simple easier integrals here. Okay, so what we can do is here is -1, 1, and you are doing the integral. The integral here is 100 you are over x, then is 100x, and then here is because here is the x squared, then you are going to the x cubic, so x cubic, and you have to times of 1/3, then it is going to be 2 times x cubic times y, right? And here you know that is x equals to 0, x equals to 2, and dy. Okay, I mean, hopefully you guys still remember what's going on here, right? So here it means you are going to insert the x equals to 2 inside this equation, and the minus you insert the x equal to 0 in this equation. Okay, so we will write these things detailedly this time. Okay, so next time I'm going to assuming you understand what this means. Okay, so then 100 times 2 minus 2 times 2 cubic times y, and minus 100 times 0, and minus 2 times 0 cubic times y, and then here is dy. Okay, so then this thing looks like is equals to 200 minus 8y squares and dy. Okay, so what we can do here is like, okay, then what we do is we are gonna to doing the integrals. Here is the 200y, and oh no, I'm sorry, I just make a mistake. Here is 16y minus 8y squares over the -1 and the 1. Right, then here this is the so then here is the, let's see, so what we have is this is equals to 400. Okay, so yeah, so this is the solution for the example 1. Also, I mean, you can do the integral in the other ways, like you can integral the y, like, so you can doing the integral is like you can doing the integral on y first, and then you're doing the integral on x. So here is if you are want to doing the y first is this way. So but this is but the thing is that it really depends on you. If you think which one is easier, you can do that integral first. So okay, so then okay, I'm gonna to skip all the detailed parts for the integrals, and so this part is going to be 400. Okay, so then let's see about this. So give you a chance. Okay, so let's see using the in-class practice. Okay, so this is an example in our textbook, but I do want you guys to doing this as an in-class practice. So you have find the volume of the region bounded by the elliptical paraboloid z is equals to 10 plus x squared plus 3y squares, and below by the rectangle R, x region is x belongs to 0 to 1, and y belongs to 0 to 2. Okay, what about, I mean, just getting the multiple integral for this part, for these questions, and then we are doing this as the in-class practical, because we will actually we will definitely have a similar questions. I mean, definitely have a similar questions in our filling the blanks actually for these questions. Okay, so it's like you have to understand how to do the double integral in a rectangular space, okay, on a rectangular area. So let's get in like 5 minutes to do this in class practice, okay?
4G আছে কিন্তু স্পিড কই?
এভাবেই তো চলছে।
শুধু চললে হবে? এগিয়ে থাকতে হবে না?
In this video, we're going to talk about how to find the partial derivative with respect
Professor
to a
Dave
certain
again.
variable.
Let's revisit
So
integration.
for example, let's say if we have a function that consists of multiple variables, in this case x and y. And let's say it's equal to 7x squared minus x cubed y to the fourth plus 5x to the fourth y cubed. So what is the partial derivative of this function with respect to x? How can we find the answer? The partial derivative with respect to x is symbolized by the variable f sub x.
So this
Now, in order
question
to
is,
find it,
so when we're writing writing down
other
the solutions
variable,
here, so if
in this case
I mean,
y,
if
we
you
need
want,
to treat it
this
as
is
a
in the
constant.
calculation or in the application
You only
question.
treat x
So
as the variable. Everything else, you
actually,
view it as a
so
constant.
this is
Now,
is
before we do this
starting a
problem,
good
let's
start
review
for
the
the double
problem.
integral is actually you
Let's say
understand
if we
what is
have
going on.
a function
And
x
but
to the n.
I mean
If we wish to find the
this is part is not a mandatory. Okay, this is not mandatory. So usually it's like you as long as you I mean you writing down this part. Okay, if you as long as you're writing down starting from this part, it's like you know is so what is the I mean the region of y and what is the region of x, and then you do the integral, and that will be fine for you. Okay, so this is this is a kind of how to say, it's like a pretty simple question for you guys. So it's like just saying, okay, you are, because this is rectangular, so it is on a rectangular integral area. So there's no restrictions, or there's no relationship on the integrated area between I mean x and the y, they don't have relationship on the integral area. Okay, so then what you can do is you can just simply putting the dy and the dx, and still the same thing. I mean, you know that, so which parts of y, so you integrate the y first or integrate the x first. So here is we integrated the y first, and then after you integrate y first, and then the second part you integrated x. So as long as as long as you know that when you are integrating y, and you should treat it our x as a constant. So when you do the integration, so x is just a constant, and then you know how to do it, and then you goes into these steps, and then you know that, okay, yeah, then it goes into these steps, and x is not a constant anymore, and x is a variable, and then you integrate on x. So you will pretty easy to get the final solutions here. Okay, so the multiple integral question. So this is just a very easy rectangular integrating questions in our examinations, right? So typically, I mean, I will not put these kind of the rectangular questions, rectangular area integral questions in our calculation or in our proof or application questions. So typically, it should be just inside filling the blanks. As long as, I mean, just to see whether you have a good understanding for what is the multiple integral is. Okay, so just it's only usually it's just inside a filling the blanks question. So then, okay, so then what we are going to do is we're going to do the next part. So for this part, is we are going to so I'm going to have to put those the calculation or the application questions from this part, because so you are going to understand, okay, to understand how is you are going to do the double integrals over the general region. So this is my requirements for our calculations. Okay, so then let's see. I'm going to share the screens for the slide. Slides. no, this part. Yeah, so we're going to share the slides for the section for 15.2 is about the double integrals over the general regions. So previously in our textbook is that we are going to integrate the region over a rectangular space, such as in the the red rectangular. So the x and y, they don't have the you don't have to considering like how x and y they are changed and whether it will affect the integral range. However, if we go into the and so if we see here is we see the figure 15.8, and we can see. Just give me 1 minute. Okay, so we see that rectangular grid partition a bounded non-rectangular region into the. So here is like we can see here is. So we are trying to do what? So we are trying to using a rectangular grid, to partition a bounded non-rectangular region into the rectangular cell. So when we see this, if this is the when we see this is the general range, okay, so it's no longer a rectangular range. Okay, so then fxy is positive and continuous f over r. So we define the volumes of the solid region between in the figure 15.10, which is bounded above and below by the curves y is equal to g2x and y is equal to g1x is on the sides by the lines x equals to a and x equals to b. So we may again calculate the volume by the method of slicing. So we first calculate the cross-section area. So first we calculate at the cross-sectional area. So ax is equals to y equals to g2x and y. So you are integrated fxy from y is equal to g1x and g2x, and then integrated x from x equals to a, x equals to b to get the volume as iterated integral. So v is equals to, so you integrate from ab and gx, g2x, or fxy and dy and dx. So similarly, if R is a region like the one shown in figure 15.11, bounded by the curves is x equal to h2y and x to h1y, and the lines x equal to c and the y equal to d, then the volume calculated by the slicing is given by iterated integral. So let's see here. So previously, okay, so just see this part. So previously in this integral, right? So in this integral, so I mean the area, the regions of the integral, we know that this is a rectangular. So if this is a rectangular, so what we can do is, we are still doing the same thing. Is we are trying to add up, right? To add up all the small slicing, right? The first thing is that we have to know what the area of x, right? We have to know what the area of x. So after the curve actually is the curve, right? The curve below the curve below, and so starting from, we're looking from the x-axis, so XOZ plane, and we know that this is a small segment. We add up the infinity small segment, and then we transfer our side, and then we can see a small. And we are trying to add up those small slices together. So it's the same thing for the general regions. So here is like we see here. So you see, if you can see here is that we are so the region is no longer, right. So the region is no longer rectangular anymore. However, if we starting the things from the previous one, and we look at it here is we are keep going is we are still assume, right, that x is from a to b, right. We are trying to add up all the small slices, right. We are trying to add up all the small slices of all small slices when we fix the x area, right. So now it's like what we can do is we need to know what is the area of each small slice, right. Now, so suppose here, so if we are trying to say this small slice, right? So what about this small slice, right? What is the area of this small slice? So because, so here is a curve, it is no longer, right? These two curves, they are no longer segments anymore, they're just curves. So when it is a curve, which means this, the value of this part depends, right? Depends on x. So the value of x will depend on, will decide how long this segment looks like. How long is this segment, right? So the minimum is from G1x, right? The minimum is from G1x. The maximum is from G2x. So then so actually it's G1x and G2x actually are these two curves, right? These two curves and the projection, okay? So the projection, okay, so the projection is on the XY plane is there. So then what we know is, so we have two different gx1, gx1, and gx2. So then we know that, okay, so the y, the length of y is restricted by the y1, g1x and g2x. So the area here, so the area here, right? So what you have to do is you have to calculate. So you have to, so actually, so I mean, if we just seeing the slice here, okay, so we're seeing the small slice here. So we're seeing the y is here and z is here. So this point is the g1x, right? This point is g2x. So you have, so actually this point that depends on how x looks like. I mean, how the x define the y, right? So this is the area. So we are transferring the area here. Okay, so now, I mean, going back to the rectangular area. Okay, so we are knowing, so we know, so here is we know that, right? So here is where, so if we look at from the XOZ plane, and we know that, so it's like, so for the specific x, and we know what is the y, what is the area is, because however, the region of y, right, is not depending on x, right? If you can see here, so for any specific x, y is always the domain of y is always from 0 to 1, just because this is a rectangular. Now, if the y is no longer the rectangular is here, so for a specific x, y is decided by the value of x. So that is why we have the region here, right? But the area here is always depending by this part, right? So when you are fixing x, so if you are, for this small area, so z is equals to fx0y, right? So for here, right, for this one, so now you understand. Okay, now you can see that. So if as long as the x is fixed, so the area of this small slices is also fixed, and then you know how to do this. So then I'm using the formula before. It's like, so I mean, previously it's like we only have fxy, and the limits of the integral, the upper limit and the lower limits of the integral previously is just, I mean, is just decided by y itself, but now is decided by the x. Okay, so this is what we discussed in the previous slide. So then if we see this plot here is like, so now previously the slice is fixed. When we fix x, so we are trying to get this small slice to see how this, and get small slice from the y and z. And then now it's like we will trying to fix y. Okay, so when we are trying to fix y, so we still have, if you can see here, we still have two curves, right? So one is h1y and h2y. So here, so it's still there. So if you fix, so you have to say, okay, so y is y0 here. Okay, so then we still transfer it into the two-dimensional space. So here is the y, right? And so what we can do is, so here is x and here is the z. So we fix the, so here is the h, 1 y0. Here is h2 y0. Okay, so although this y can move, okay, y can move from C to D, but here for the specific y0, then we know what is the integrated area for the x, and we know what is the surface, okay, what is the curve of z, right? Z is equals to f x y0. Okay, so now y is fixed. So then the volume of the solid shown here is integrated from C to D to ay dy and equal to cd and h1 to h2y, so fxy dx dy. So for a given solid, theorem 2 states we can calculate the volume as in figure 15.10 or in the way shown here. So both calculations have the has the same results. So so from here, I mean, this is just giving you a concept how these things looks like. Okay, so then is we have the theorem 2 is Fubini theorem. So this is the stronger form. So let x, y be continuous on a region R, and if R is defined by x belongs to A to B, and g1x is less than or equal to y, and y is less than or equal to g2x, with g1 and g2 are continuous. Okay, so I mean, very important. Okay, so G1 and G2. So this is pretty important. So when we are doing though these how to say, so when we are doing this type of the question, so we are always have the assumption that G1, G2 they are continuous. Okay, so this is so in the advanced mathematics, so usually we don't emphasize on these conditions, but so because I mean I'm learning the analysis, so I'm learning the analysis not from the not saying the calculation. So when I'm in the grad, so when so for all of these things, so we are very very careful when if the condition of the G1 or G2 they are continuous. So this is pretty important. So then so f is defined by y. So then hy is less or equal to x and less than or equal to y, h2y. So with h1 and h2 are continuous on C and D. Okay, so from this Fubini theorem, so a very very important thing is here, right? So it is like so it's actually it is the same thing as a rectangular area, but in the rectangular area, because x and the y they're independent, right? They're independent. So for the x and the y, so it is okay, like you want to define the x or you want to define the y first. However, in this general region or the Fubini theorem stronger form here, so if you can see the theorem here is like you define one variable first, right? Then you have the other variable, which is the its integral area is defined by this x. Okay, so if you based on this theorem or based on this definition, so when you are trying to do the multiple integral in a general space, so you have to be very very careful. So what is very important is, so you have to be very careful. Is like, so you have to understand that, so when you are trying to define an integral range or integral area, so the first thing is you have to define the the range of one variable first, no matter x or y. So and then you have so step one is you define the area of x or y. This is the step one. And step two, based on the range of the x, and then based on the condition you might see in the future questions, and step two, then you find the region of the other variable. So very important thing is you should always precisely know what the area is. Okay, so let's see this example. So this example is actually is example one in our textbook. However, I want to use this example to show you like what is the definition. So what is the meaning of this theorem two? Actually, is fixing one and then trying to calculate the range of the other. Okay, so let's see here. So a prism with a triangular base in the xy plane. The volume of this prism is defined as a double integral over R. To evaluate as an iterated integral, we might integrate first with respect to y and then with respect to x, or the other way around. So let's see. So here is here is the here is the prism, right? The prism is here. So so the area in downwards, I mean, the area on the x or y plane, and here is, we can see here x or y plane, right? So x and y, right? The x or y plane is x is equal to y, and the plane is let's see, the plane is actually is the total area actually is y is less or equal than x, right? Let's see. Yes, y is this is here is y is equals to x, and this. So actually, so when you are doing the multiple integral, so for whatever reasons, so you have to see what is the, what is the down area, like what is the projection area of the total surface. Okay, so the projection area here is this, so this part, okay, is this part. So what you should do is, when you know what is the projection area, right? So then you have to, okay, you have to draw the graph. Okay, you have to draw the graph like this. So I mean, B and C, there are two different ways, to have the slides. So the first thing is you have to understand. Okay, so if we don't want to discussing these things into the three-dimensional space. So if we, I mean, because it is not a triple integral. So for a double integral, so if we don't want to discussing this into a three-dimensional space, so what we can do is we need to know what is the integral area is. So the first thing is we need to plot the integral area into on the relationship between y and x. Okay, so let's go back to see here. So okay, so we say that step one, we have to define, right? To define the area of x, or we have to define the area of y. So the first thing, if we define the area of x, okay, so we define x here. Okay, the step one, right? So we define x. So where is x? So looking at this area. So if we want to cover, right? If we want to cover this blue area, what is the smallest range of x, right? So the smallest range of x is belongs to 0 and 1. So x belongs to 0 and 1. Okay, so now for this part, okay, so now you already set up the small range for x, right? Belong 0 and 1. Okay, this is just for the learning. Okay, so now you know that x belongs to 1. Okay, the next step is you have to define, right? The step 1. Then what about step 2? Define in the area of x belongs 0 and 1. So what is the range of y, right? So here, okay, so for each fixed x here, right? For each fixed x here, so you just draw a line here, and you find that, so you find what? So y is, so the upper limits of y is y equals to x, and the lower limits of the y range is from 0, right? Is x equal to 0, or we're just saying that y is equal to 0. So from y is equal to 0 to y equals to x, then you know that, okay, so the step 2 is y is equals to 0 to x. Okay, so when you know that, and then what you need to do is you are using this step 1 to write down. You just write down the double integral, multiple integral, the function. Okay, so you know that x belongs, so because you are, so step 1, you are defining what is x belongs to. So now outside you have to put in the x equals to you have to put x equals to 0 and x to 1 first. Okay, so this is outside, right? This is the outside. Step 1, you are defining the outside. And the step 2, you have to define the inside. The inside is from 0 to x, fxy dy. Okay, did you see the step? So the step 1 is like you are trying to find the area of x. right? So then it's going to be the outside of this integral, okay? And then you are finding, you want to find the specific area of the y and based on x. So then this is the, so then you are putting them inside of this integral equation, or in this integral, okay? So how about if you want to fix a y first? So here is the fix a y first. So fix y first is here. So step one is, what is the smallest, the smallest range of y which can cover this blue area, right? Which is the smallest one you can cover in this blue area. Okay, so here is a y. You see here is, right, these two. We know that as y is from 0 to 1. Okay, we know that, okay, y is from 0 to 1. Now we need to still the same thing. If we fix the y0 here, so we find the other slide, fix the y0 here. So, and we draw another line. So okay, so what is the area of x? So this time we know that, okay, step 2 is, what is the area of x? So the smallest x, right, for this specific y, the smallest x is y0, right? The largest y, the largest x is 1. Okay, so now this is, did you see this, right? Okay. Did you see this? So it's like, so this is how you are going to define the area of the integral. So if you can see here, like, so I mean, in the if you are fixing the x, so if you fix the x first, this is the integral, and if you fix the y, and this is the integral. So you can see here they are different, right? Although the outside is always, right, like it's always 0 and y. However, the relationship of y and x, they change when you are changing the, when you are trying to changing the integral order, right? Did you see here? I mean, actually, this is very important. So when you're trying to to exchange, to exchange the integral order, you have to understand, you have also have to change the upper limits and the lower limits of the integral. So this is pretty important, okay? So actually, if I have a question, it's like sometimes is, so it is like, so sometimes, I mean, if it is like, so if you are just, so if sometimes, so the question is, so you integral on x first is much easier than you integral on y first. Then you have to using the techniques here is to transfer the integrated order. And when you are doing the you exchange the integral order. So when you are exchange the integral order, you have to understand that. So the integrating the integration upper limits and the lower limits, they're different. Okay, so, and this is what this is really, really important. Okay, so let's see, let's using the let's using the example in our textbook here. Okay, so So the solution. So for this solution, I mean, I'm going to give you an example like how we're going to find. Okay, so previously I've already gave you actually trying to give you how is these things, how I'm going to find. So is that so for this multiple integral in a general range, so for whatever reasons, so I mean the most important thing is trying to find the integral range. Okay, actually the integral, the surface is not that important, but the integral range is really important. Okay, this surface is like you're just putting them inside the formula, it's fine, but what's the most important thing is to find the integral range. Okay, let's see how is this problem define the integral range. Okay, let's say bounded by the x-axis and the line y is equal to x and x equal to 1. Okay, so I mean what we can do here is like, okay, so I mean because this is like you have x or y, right? X y, and it's saying that it is bounded by the x-axis. So okay, x-axis is here, okay, so which is y equals to 0. Okay, then it's telling that it's bounded by y is equal to x. Okay, y is equal to x. The third thing is y is equal to 1. Okay, y is equal x is equal to 1. So now, so we find, okay, now we find the area, right? So when we find the area, what we can do is, okay, so now we have to define how the area is, right? So then we're saying that, okay, what about x is, so it's like, so usually we're just starting from x. Okay, starting from x is how the x looks like. So, okay, so here is, you are fixing the x. Okay, so we want to find what is x. So x is here is 0 and 1, right? We find x, so the x is from 0 to 1. Okay, 0 to 1. So 0 to 1, right? So 0 to 1. Okay, so we know this is this range. Okay, then we fix x. Okay, so 0 to 1, x is already there, right? Then we need to discussing what is the y looks like. Okay, so then for the y, we are fixing x. So fixing x, fix x 0. So what is this slice here? The slice here is, right, so from here is 0, right? So y is from 0. Here is y is equal to x. So from 0 to x. And then you just put fxy here. Okay, what you can do is there. And then you just are doing the integral for 0, 1, 0x. And then you put 3 minus x minus y dy dx. Okay, so here, very important, the other very important thing is here. So when you are doing the double integral, right? So what I'm always asking you guys to do is, if you are integral y, x is constant here. Okay, x is constant. Keep in mind, x is constant if you are integral on y. So then here is 0 to 1, right? You have to make sure that x is constant. So then the inside is going to be 3y minus xy minus 2 over y squared over 2. And so here is 0 and x, here is dx. So now, I mean, for this part, okay, for this part, x is still constant. Okay, x is still constant. So then what we can do is just we are putting the x, so insert y is equal to x and y is equal to 0 there, and then we're just saying that, okay, so now it's to be 3x minus 2 over 3x squared, right, dx. So for this time, the x is, so for this time, so x is the, so actually x is the, how to say, x is the variable, so it's no longer constant anymore. Then you're just doing the integral. So 3x is 3 over 2x squared minus 2 over x third, and x is equal to 1, 0, and finally it's equal to 1. Okay, so this is the solution for our example 1. I mean, similarly, you can do this for the using, if you are fixing the area for the using the slide. So we are fixing x, or you can do in fixing y. It's also the same. Okay, so then we have to giving the example 2. Okay, the example 2 is a little bit, so I mean it's using the same thing, but it's a little bit, I mean not a little bit different. Okay, so let's see, calculate. So let me think about this. Okay, so let's do this in class practice. So calculate the double integral here, sin x of x dA. So where R is the triangle in the xy plane, bounded by the x-axis and y equals to x and x equals to 1. Okay, so let's using like maybe like 5 minutes to get to try to solve this question. Okay, so now this is so actually this is the example 2 in our textbook. So very important thing is I mean I want you guys to find the integral regions of this question. Okay, so this is I would say this is pretty simple. Okay, so this is pretty simple as long as you can find the integral, find the integral the integral region. Okay, so so for this question, I mean, it is the same thing as that you have to, you have to make sure, you have to make sure what is the integration area, right? So the integration area here shows that. So the integration area here shows that. So if so, let's see. So here is the integration area. Here is the let's see. So the integration area shows here is that, so one is the x-axis, and there is x equals to 1. The third is 1, y equals to x. So actually, it still is this triangle area, right? So, I mean, first we can fix, right? We can fix the area here, like fix x is belong to 0 to 1. And then we know that fix our x0 here. Then we know that the integration up limit and the up bound and the lower bounds here is the 0 and here is the x, right? So then you can just transfer this integration area into the integration formula. And so what you can do is, that you fix x first, then you just put x outside this. So put the x in the outsiders, and then you know that the area of y is from 0 to x, and you can put the y insiders, and then you are trying to calculate the the integration of the just integrating on y, and finally you get these answers. Okay, so this is a pretty basic theory of like a pretty basic how to say questions for how to do the integration. Okay, so then, so I mean, this is usually is like, so for how to do the double integrals over like the general regions, because all these regions, at least still is a triangle. And for the next part, not here. So for the next part, we are going to. So for the next part, we are going to discussing is like find the limits of integration. So so for now, it's like I haven't decided is whether our multiple integration will be so just for the double integration, it will be restricted within those triangle area, or as like just following a restricted area, which is actually is bounded by the x-axis or y-axis, and with it looks like it was a triangle area, because at least you can always find the area with the help of the axis. So and now, so we are going to our final exam is going to extend this to this the limits of integration. We're integrating first with respect to y and then with respect to x. Okay, so it's like so in our so how to say, it's like so the previously the integral, right? The integral is always like so you can have the you can with a actually it's just a let's see no not here it's just you always find the area. Okay, so for example it's here, right? So something like this, or sometimes I mean is more simplified is just like the integral area is like this. So actually all of these things you can get the help. So finding the area again with the help of the x-axis or y-axis. However, I mean, in the most of the case, is like you can find those integral areas by two curves. So which the curves, which these curves they can let me see. So which this curve can decide the upper bound and the lower bounds of the integration. So for example here, right? So here is I have two curves. So one is x squared plus y squared is equals to 1. So right, so originally, so here's this. So this is like this. So actually this is a circle, right? This is a circle. And then the other curve, or we're just saying the other line is x plus 1 is equal to 0. Right. So the other curve is x. Okay. Yes. So this is so this line is x plus 1 is equal to 1, and the curve is actually is a circle is x squared plus y squared is equal to 1, and it is actually is asking you to have this small area which is which so this area is which is how to say is which is defined by the circle. I mean in the as in this small area. Okay, so actually, I mean, if we are discussing, I mean, the other area, that's the next thing, but we don't discuss here. So actually, we want to figure out how is these things works, right? How this thing works. So the first thing is like, so for this small area, okay, so what we can do is we can first we can think about it is like, so we have two different tools, right? So in our hand we have two different tools. So one is we fix x and get the slices of y, or we can fix y and then we get the slices of x. So the first thing is we can do, so what we can do is, so we try to fix x. Okay, so we try to fix x. So if we fix x, so we still, I mean, when we are trying to fix x, so we don't think about how this graph really looks like. So what is the exactly what is the exactly graph of the area looks like? So we never care about this. So we only care about is when we are trying to fix the x first. So we want to know what is the smallest range just can cover this small area. Okay, so the smallest range here telling us is that the smallest range is x is belongs to 0 to 1, right? X is belongs to 0 to 1. Okay, this is the smallest range, right, of x. So after we know what is the smallest range of x, then we say, okay, what about we just fix x0, right? We fix x0 first, and then we draw a line which is perpendicular to the x, or is like, so we draw a line which is x is equals to x0, right? And then we can find what is the limits, the upper bound and the lower bound of y. So the lower bound here is y is equal to 1 minus x, and the upper bound here is y is equals to a square root of 1 minus x squared, right? So then we can find that, okay, yeah, what is the, so then we're just saying, okay, we fix x first, right? Is 0, 1. Okay, so then we write down dx, and then we have the y, and we know the y area. So y area is from the 1 minus x. So the upper bound is square root 1 minus x squared, and then we have fxy. Okay, so this is how we get the integrating area. So kind of a little bit difficult than the previous examples. Okay, so then here is we're trying to integrate it from the y first, so we fix the y first, and then we want to find where's the x. So the first thing is still, I mean, if we want to fix, so the same thing is if we want to fix a y first is always find the smallest range of this y, which can cover this area. So it's like, so we still see, okay, y is here, right? So still, I mean, don't never, so actually even in this time, so in this time, so you should always never cares about what is the real, what is the what is the real, how to say, just like don't care about what is the area looks like. Just the only thing you need to know is to make sure that this is the smallest range of y which can cover this area, right? So y is belongs to 0 to 1, right? So y is belongs to 0 to 1. And then you fix y0, okay? Then you fix y0. The next step is to fix y0, and then you draw a line which is equal to y0 and y. So the lower limit, the up limit, and the down limit is depending on the x-axis. So you are from x from 0 to x. So you are from, so x is, so for this line it's from 0 to positive infinity. I mean, always, I mean, you know, it's from, or you can say this is from the or more, as we can see, it is from the negative infinity to positive infinity. And then you from the negative infinity to the positive infinity, and then you find the specific points where y equals to y0 intersect with this area, and then you find this point. So this point telling you that this point is x is equal to 1 minus y, right here. And then you find that the other intersection where y equals to y0 is that is, so is the this perpendicular line is going to give, you know, it's going outside of this range. So here is x equal to square root of 1 minus y squared. So you know that, okay, so we define the y, right? So 0, 1 dy. Then we define x. So x is from 1 minus y to square root of 1 minus y squares and fxy. Okay, did you see that? So this is so for this is like, so always you have to keep in mind that, so it's like, so for the double integrals, you have to find the integral area. Okay, so find the integral area first, and then if you want to integrate, so if you want to find the x first, then you find the, you know, find the area of x, or you want to do the y first, and you whatever. So I mean, it depends on how you understand it, okay, or how you want to try to do it. So you can fix y or you can fix x. So if you want to fix x first, then you have to find the smallest area which covers this small, which covers the whole area of the integration. Okay, and then you fix x, and I mean, then you find the line x equals to x0, and you find the lower bound and the upper bound of the integration part, and then finally you can write out this integration formula. Okay, so this is the same thing here. It's like, so I mean, we might discussing some example next time, but this is like just letting you know that how are you going to find the do the multiple integral, okay, for doing the double integral. Okay, so this is all for today's class, and that's it. See you next week. So I'm going to send out the homework for today's class before Wednesday. Okay.
Thank you, Laush.
Yeah, you're welcome. Yes, what you want? The whiteboard. Okay. Whiteboard. Okay, just can you see it? Yeah, just Okay, yeah. So yeah, the class is over. Thanks.